This diagram displays a standard two-dimensional Cartesian plane. Here, straight lines are bound by absolute constraint. They either intersect or align in perfect parallel. Introduce a z-axis, and the geometry expands. Lines that appeared to collide separate vertically, opening a distinct spatial gap. These are skew lines. Because they inhabit entirely different spatial planes, they are neither parallel nor intersecting. The objective is isolating the exact mathematical method to pinpoint the absolute minimum orthogonal distance between these two isolated trajectories. This 3D coordinate space models two skew lines using parametric vector equation, r equals a plus lambda b. Variable a is the position vector, mapping where each line begins from the origin. Variable b is the direction vector, projecting forward to dictate the infinite trajectory. Because skew lines exist in continuous 3D space, visual estimation fails. We rely entirely on vector algebra to mathematically isolate the gap between them. By clearing the coordinate space of the physical paths and positions, we can analyze just the two direction vectors, b1 and b2, originating perfectly from 0, 0, 0. The spatial angle separating these infinite paths is evaluated directly using the dot product equation. Measuring the distance between arbitrary points along these paths yields infinite variations. Point-to-point measurement cannot identify the minimum threshold. Strict geometry dictates that the absolute shortest path connecting two skew lines must run perfectly perpendicular to both trajectories simultaneously. Generating a single vector perpendicular to two independent directions requires a specific operation, the cross product. Executing the cross product of b1 and b2 violently extrudes an entirely new shared normal vector into the 3D space. These geometric squares confirm that this new normal vector maintains a strict 90-degree offset from both original directions. Reintroducing the initial position points, A1 and A2, anchors our normal vector environment back to the specific locations of our skew lines. Subtracting position A1 from A2 constructs a direct, arbitrary connecting vector across the empty space. This connecting path is diagonal and jagged. It represents a distance, but its inefficiency guarantees it is not the shortest distance. To compress this path down to its most mathematically efficient length, we execute an orthogonal projection. Projection casts a geometric shadow of our connecting vector onto the shared normal vector. Calculating their dot product quantifies this shadow, forming the numerator of our equation. Placing the cross product magnitude in the denominator normalizes the vector math into a pure scalar distance. The absolute shortest distance between two trajectories is strictly deterministic. It is extracted by mathematically projecting their positional difference onto their shared normal axis. This exact mathematical operation serves as the core safety engine monitoring complex physical engineering systems. This generated video captures a solitary satellite navigating low Earth orbit. Aerospace systems must track multiple objects traversing distinct linear trajectories at varying altitudes. Air traffic algorithms constantly evaluate this shortest distance equation to find the closest point of approach. If the orthogonal distance drops below regulated safety thresholds, automated systems immediately trigger collision avoidance alarms. This extreme close-up image of intricate copper traces on a circuit board scales the same geometric logic down to the microengineering level. A copper trace routed on layer 1 and an overlapping trace routed vertically on layer 2 function geometrically as perfect skew lines. The physical thickness of the FR4 dielectric material sandwiched between these layers represents the literal calculated shortest distance, d. If that calculated distance is mathematically insufficient, the hardware fails. The overlapping signals will induce capacitive crosstalk or trigger high-voltage arcing across the dielectric gap. The exact same vector projection equation preserves system integrity, whether preventing a mid-air collision in the stratosphere or a short circuit on a silicon board. Moving from physical engineering, this calculation drives the digital environment of 3D rendering engines. A virtual camera ray cast as line 1 maps spatial proximity, barely missing a polygon's hard wireframe edge acting as line 2. The engine evaluates this near-miss floating point distance, using tiny numerical gaps to assign precise anti-aliasing weights, softening jagged shadows into smooth gradients. Executing these spatial solutions requires flattening the continuous geometry into raw, discrete programmatic instructions. This split screen compares the theoretical projection equation against the cleanly formatted Python verification code, defining variables for the dot and cross products. The script evaluates the analytical distance, setting up a linear system to compute exact 3D spatial coordinates, where the orthogonal segment locks on to both lines. The vector calculus of skew lines provides the universal computational engine required to translate abstract 3D space into engineered, actionable reality.